Hello and welcome. Here we are in lecture 14. So today we'll be getting back to covering new language features and new ways we're using hardware design. In particular, we're talking about inheritance. So all quarter you've heard me extol the virtues of using Chisel for hardware design and saying you get the full power of Scala, including its functional programming and object-oriented features. And we have made use of both, right? In particular, the object-oriented features, right? We've been kind of encapsulating things in modules and bundles, and making our own bundles. But we kind of not been taking full advantage of the object-oriented features. And we're going to change that today. We're going to try to take advantage of something called inheritance, which you've probably seen in your programming classes, where you can not only define types of classes, but you can extend them and do some really cool things, right? In particular, you can declare things once and then reuse it in different ways or override it. And it's really powerful, right? That's kind of what we want from our code. We want to reduce duplicate code. We want to make it easy to interact with things. And if things are somewhat similar, well, perhaps we can make them somehow the same type. And inheritance is the way we can do that. So instead, we're going to first cover some of these concepts in Scala, show some examples of how we use them in Chisel and hardware design, and then close out with the thing we left the cliffhanger from last Wednesday. Remember, we did our queue and we made our queue so much better after iterative design, but the last feature that was missing was type parameterization, right? Where our queue could take an arbitrary bit width for its input, but it had to be a uint, right? And in order to parameterize the types, we need to learn a little bit more, and well, a little bit more is going to be just today. So we're going to go ahead and make our queue totally set. And if there's time at the end, also we'll preview some of the things to be aware of for the project coming up in the coming weeks. So let's go ahead and load up a notebook. Cool. And so, yeah, why use inheritance? Or I should say, object-oriented inheritance. Well, really, it's a matter of increasing productivity through reuse, right? You can recognize that, yes, there's common components, then rather than rewriting them, I can write it once and share it, right? And you've already done that, for your careers in programming. Oh yeah, this is a common feature. I should put this into a common object or a common function or something. But when you start having objects, sometimes you kind of want to capture some of the object properties in the reuse, right? And so, in particular, when you think about reuse, you should be thinking about, okay, well, I have these various object types I want to be working with, and even though they're technically different types, and I want them to be different, there's sometimes I want them to operate the same, right? So what does that mean? What does that take, right? Or you know what? What if I have things that actually always behave differently, but I want them to have a common interface, right? So that way someone can design their code on one end or particular their hardware on one end to talk to a certain interface. And even though you can just swap these things on the other side without needing to recompile or change anything, right? So these are kind of the common things we're exploring, right? Reusing functionality, reusing interfaces, and where things are similar and where things are different. And so when you're programming, there's all sorts of scenarios that can come up about, oh, I want to use this, I don't want to use this, I want to have this trait happen, I want to have... And so as a result, Scala's got a lot of mechanisms for inheritance with object-oriented programming, right? There's a lot of different subtle nuances, a lot of keywords. We're going to cover only a fraction of them, but it'll be a powerful subset. You'll be able to do quite a bit with these. So, first off, let's talk about straightforward class inheritance. We've actually kind of already been doing this and maybe perhaps not even been conscious of it, right? So we've already seen this class. You can go ahead and declare a class, and these are kind of, the arguments that are used when you create that instance, right? And the entire body is evaluated. It can have, code by itself. It can also have, define some methods to work on it. So in this case, let's go ahead and define a class and, have a phrase that we use in a greeting function. Okay, so it's going to print, hello, and actually the name, where does the name come from? The name comes from the argument it's constructed, right? So internally, this is going to have, some internal state for this class. It's going to be the name, and all classes of, type parent are going to have this phrase hello. Okay, so, and then if we go ahead and run this, we're going to see, hey, yes, we instantiated a new parent called Kate. And so we get hello Kate when we call .greet. Now let's say we want to make a child class. And so we're going to extend the parent class. So what that means is we're going to, at first, get everything the parent class has. Now, if we want to differentiate the behavior, we can override one of those fields, right? So we can say, you know what? I know the class I inherited from has a thing, something called val phrase. No, it's a val, it's called phrase. You know what? I want to override it with my value, right? I want it, when you receive my instance, I want you to use hola rather than hello, right? So now, of course, when you create this child instance, let's say we call it Pablo, you get the greeting hola Pablo, right? And so yes, so this is pretty cool. And so we've of course seen this extends keyword quite a bit already. We've been extending module and extending bundle, and that's kind of how Chisel works, right? Is that they've defined Chisel, module, and bundle, and we're extending those when we make our own instances, right? Another thing to point out is that when you extend, at the time you say extends, you can give arguments to that class, right? So parent takes a name, so we can give it that name, right? If we, for example, omitted that, I'm pretty sure it's gonna give us an error. Yeah, because we're like, you know what? Parent needs a name, and you can't do one without it. Cool. Another detail is you may have seen this differently in other classes, but in Scala, by design, you can only extend one class, right? So if you need to inherit from multiple classes, this kind of class inheritance is not going to be the way to do it. There's something called traits. This will make it possible, but for full-on, extending via class inheritance, that's only going to be possible from one class. And the reason why this comes up, you can look at this in the literature, is there's something called the diamond problem, where you can imagine if you have a class, and let's say you have two parents, then you inherit from both of them, and then what if those two classes inherit from something else? You can imagine you get these arbitrary topologies of these inheritance graphs, and you can end up with cycles, right? Or you can end up with just ambiguous ancestry, right? And so by having a single parent, you give you a clear precedence order, right? So if you have two parents, it's like, okay, and they both define something, well, which one do you get, right? You're kind of matching them together, and well, which one does the child class get? Could be hard to kind of define the semantics. With a single parent, you can do precedence order, right? So, hey, my parent two classes up defines this, but also my most immediate parent defines this. Well, perhaps it'd be logical that the most immediate ancestor is the one that should be the one that should win out, right? And so, yeah, there's a lot of language semantics reasons why single inheritance makes sense. And like I said, fortunately, something called traits we'll cover in a few minutes. You can handle the cases where you think you might need to have multiple inheritance. Cool. Okay. Questions so far? Great. All right. So in this first case, parent's a completely valid, concrete existing class. In contrast to a concrete class, you can have something called an abstract class. And you may see this in other languages. And the idea is you can have a class that you intend to only use via inheritance, right? So an abstract class is something that you cannot instantiate, but you can still define plenty of stuff inside of it. That's why you're doing it, right? So you can go ahead and define things you're going to override. You can go ahead and define common functionality. And so now with this, abstract parent, I can go ahead and extend it, right? And so I can say, hey, I want to make, perhaps make this child class is concrete, right? So when you have an abstract class and you extend it, you can make it concrete. There's no abstract keyword here, so that makes it concrete. And yeah, so I'm, this case, providing a value for hello. And this actually is kind of a little bit interesting, right? Because if you think about it, wait, phrase is a val. And here we don't actually define it, right? We don't actually give a value for it. We declare it. We say, hey, I'm going to have a val that's going to be called phrase. That's going to be of type string. But there's no value given here. So it's really just like a pre-declaration, right? Which is only something we wouldn't see in a language like Scala or Java, right? But yeah, that's what we're doing. We're saying, you know what? Things that inherit from this abstract class parent, they're going to have this field called phrase. So notice how in the child class, not only do we assign a value to it, we don't even have to call override, right? And so that's kind of a little surprising, but yes, this is going to work. So we can go ahead and make our, this class, we can go ahead and define, hello. And then we can also, once again, do the same thing as we did before. we get hello Kate and hola Pablo. And so in this case, we have, two child classes that both are inheriting from parent, right? And, as you can see, of course, that they change the value of this field. They still have kind of their own internal field for their name, etc., right? And so, yeah, let's say, for example, I tried to say, hey, give me a instance of this abstract class. We're going to see it tell us, no, I can't do that. Class parents abstract cannot be instantiated, right? So some of you may be thinking, oh, wait a second. It seems like, abstract classes are, strictly less useful, right? Because, hey, I can't instantiate it, but I can extend it. But, what if I just made a regular class and then I extended that, right? Wouldn't that be more robust or more general purpose? And the answer is no, right? There's a reason why this, nuanced abstract class is created. And there's two big reasons, right? One is that it's actually easier to write the abstract class because it's not a real class, right? I'm allowed to say things like, there's going to be a field here and not actually give an implementation, right? Or more commonly, it's going to be defining a function or a method, and you're going to give the signature, oh yes, it's going to take in these arguments and produce this output, but return type, but it's actually not going to have the implementation, right? You're kind of save yourself off the hook, right? So number one is it's actually going to be, in some cases, easier to write these abstract classes than writing a concrete base class, right? So a abstract base class is going to be good for those reasons. The second reason is within your organization or the way you design your project, you may not want that base class to be instantiable, right? The way you're kind of thinking about the things that are out there and how they will be needed and how they are similar and how they're different. There's kind of this general pattern. Sure, you encapsulate that general pattern inside this abstract class, but you actually don't want that to be instantiable, right? And so this abstract class is a way to use the type system, to use the compiler, to use the language to enforce this behavior that, you should not instantiate this. You should instantiate one of these concrete child classes. So, like I said, sometimes you might think, oh, well, it seems like an extra bit of complexity, but no, it's actually making our life simpler, right? We can use the compiler to kind of check for things and make sure no one's instantiating this base class we don't want them to instantiate. And like I said, sometimes these abstract base classes are much easier to write, right? And I keep saying abstract base class because an abstract class by itself can't do anything. It's only valuable when it's inherited, right? Thus making it a base class. Cool. Let's keep going if there's no questions. All right. So if you go dig around Scala documentation, you will find this diagram. So this diagram shows the type hierarchy for Scala's collections. In particular, this is the immutable collections. And if you look through this, you'll see some names you recognize, and perhaps some names maybe you don't. But you could imagine what they do perhaps better naming, right? So, we are frequently in this class using seeks. When you look at the interpreter results, right, you often see things like vector or list. So you can see that seek actually is abstract, right? And we're actually waiting for these concrete child classes to actually implement it, right? And so depending on how you're using it, the compiler makes a choice about, oh, would you want something that has a linear seek versus an index seek, right? So in terms of data structures, they decided to arrange their classes based on things that could be accessed linearly versus things where you want to access an arbitrary location, right? So if I start indexing into it, with the parentheses and saying I want element 2, element 3, you'll probably end up with a vector, right? You're going down the index seek path, right? And if you're, doing things linearly, just going through it, you probably want the linear seek, right? But you can see that seek itself isn't the only thing. There's actually some other things before it. So actually going all the way back, there's traversable, right? And you can see that traversal is kind of the most general, commonly shared thing. Or think about all of these collections, what kind of traits do they have? Well, it's traversable, right? And perhaps you can see it kind of all funnels through this iterable, right? So yes, this iteration pattern we're very familiar with, right? You can call a for loop on it, you can call for each on it. You can also call functional programming things like map, filter, reduce. So it turns out, if you look up where map, filter, reduce, those things are implemented, they're actually implemented via this iterable interface, right? So all of these child classes are able to benefit from things like map as long as they implement the interfaces they need to for things like iterable, and then they get map automatically because they inherit from iterable. They're able to do that. Now, the different colors and arrow thicknesses here are kind of implying what are the default collections, as well as, in some cases, these are traits rather than abstract classes. We'll come to traits in a bit, but I just want you to be aware that, yeah, it's really kind of powerful where you can kind of recognize how, at the bottom level, there's all these data structures that behave or implemented differently under the hood. However, there's a lot of commonalities, so you kind of think about what's common about all of them. And you can kind of construct this type hierarchy to kind of make sense of all that. Additionally, for the commonalities, you can also not just share interfaces, you can sometimes even share implementations for things like map, for example. And not to be confusing, but there's of course map, this functional programming primitive we've been using where you apply a function to every element. And then there's map over here in the data structure sense, which is a key value or hash table, right? Well, not necessarily hash always, but it's a key value store, right? Okay. Yeah, okay. So someone asked in chat, what's the color distinction? Yeah, so the dark ones are the concrete ones as a distinction. So that's our 5-minute primer of types in Scala, or inheritance in Scala. How are we going to use this in Chisel? Well, we're going to use it in multiple places. And to kind of appreciate that, let's talk about how we've been getting reuse in our design so far. Right? I mean, our goal of Chisel not only to have this nice language and do cool things, but to get reuse, right? By making reusable components, reusing our own projects, using other people's reusing components. We're trying to improve productivity, right? And so, number one thing we always keep talking about, of course, is we're trying to build our parameterized hardware generators, and hopefully they have enough flexibility where we can kind of use them in more places, and that's kind of really our goal, right? And even though we say parameterized hardware generators, right, it's kind of more ambiguous, right? We've seen generators that not only are just wrapped as a module, some of our generators are functionality not even inside of a module. It's just return some Chisel components via a function or an object or something. We've also seen us putting stuff into bundles, right? We've made our own bundles, makes it easier to declare interfaces and have them be very parameterized, right? If you think about it, like even though it seems so simple, but have a bundle with an optional field to have an iota is or is not included, or to have a vex and change the number of ports. That's actually pretty cool parameterization, right? And it seems so simple and natural in the way we kind of do things in Chisel, but it's actually pretty sophisticated. It's actually, dynamically, or not dynamically in the hardware, but dynamically at generation time, creating an interface, right? It's a generator. It's pretty cool. So today we're going to talk about how we're going to do some of this reuse via inheritance, right? So rather than explicitly calling things, we're going to be saying, what if we can inherit things via this mechanism, right? And so as a result, we can make our own type hierarchies and realize, oh yeah, these things are similar. I can inherit from one from the other. And we can do some pretty cool stuff. And as I said, a lot of the ways that Chisel itself is implemented is via inheritance, right? We extend module, we extend bundle, right? And what we're doing is when we extend module, we're inheriting all this code from the Chisel library about how to recognize what's happening, right? Because we're used to just doing things like connecting components. Oh yeah, I want to connect this to that. How does that get recorded? How does that get captured? There's kind of this implicit context that's created when you extend a module, and it knows how to kind of do the things, right? And so yeah, so inheritance is really powerful. Okay, so maybe as a starting point, what if we decide to create a module, make it abstract? So it's an abstract module, so you can not instantiate it, but we can use this as a way to simplify the standardized interface, right? So we can see now that here we're going to define one abstract class and two child classes. And each child classes are the modules are surprisingly succinct, right? And the reason why is they're inheriting a lot from their abstract parent, right? So what are we doing? Well, we're going to say, we're going to define this abstract class called unitary operator module. It's going to take in a width. And of course, with that width, we're going to, set the input and output width. And really, it's going to take in a single input, produce a single output. And interestingly, we're going to have a function that takes in a uint and produces a uint, so some sort of operation. And we're going to apply that function to the input and then connect that to the output. Okay. And so then how can we go ahead and actually use this? Well, we can go maybe do a pass-through module, does nothing. So our operation just takes the input and passes it right through. Or we can negate it, right? So maybe we can make a negative module, which negate module will, as you can see, negates it. So you can see there we have the Verilog. yes, it passes it straight through. If we want to, for example, do the negation, you see it does negation. So it's pretty cool, right? And well, what if I try to instantiate our base class? We're gonna get the same complaints before. It's abstract, right? You shouldn't instantiate abstract classes. But this is pretty cool. You can imagine if I have things that are similar. This is a way for me to kind of encapsulate commonalities, right? The commonality in this case is that you're gonna have a single input, single output of the same width, and you're gonna apply a unary function to the input to produce the output, right? So that's kind of the pattern we're capturing in this abstract base class. And here's our concrete example instances of it, or concrete instantiations of it. We can go ahead and make over here. Cool. Questions so far? Cool. So what can we do with this? Well, we can kind of keep building up, right? So in this case, let's go ahead and build maybe a more sophisticated base class. And we can go ahead and build a library out of it, right? So maybe in this case, our base class will now be take two operations, two arguments, two inputs, right? So we binary now. And in particular, they'll be decoupled, right? They'll be decoupled inputs, have a decoupled output. And so we're going to say, our output C is going to be the result of, A operation on B. Or maybe this might be even more correctly written as C is going to equal the op on A comma B, right? And so let's see how this kind of gets put together, right? The operations, of course, applied here. But you can see it's kind of buried inside this, right? So what's going on with all this extra code? Well, we're taking in decouples. We're going to buffer the output. So it's kind of like a squashed single element form of that queue we were dealing with. And we're going to have a bit to track if it's full or not. And so, of course, we're able to receive the inputs if we're not full, right? And we have something to share, something to output when we are full. And so our outputs can come from this buffer, right? So how we populate that buffer? Well, if our inputs are firing, we're able to make transactions on the inputs, and we're not full. And if you, then we can go ahead and apply this operation to the buffer, and then mark ourselves as full, right? And then, of course, when someone reads our output, we are no longer full. And so the way this is written, we can't produce something every cycle, the order we've done things, because this thing has precedence over this one. So, this false won't be visible until later on. Another small details. Oh wait, since we say iota a.fire, iota b.fire, in order for use of fire, a.ready must be true. In order for a.ready to be true, it must already be not full. Wouldn't that be redundant? Yes. However, I don't think this is an egregious mistake because, number one, this is the kind of stuff that the tools can recognize and do Boolean algorithm simplification no problem. Number two, it's actually almost in some ways better to be extra verbose and redundant here because you can imagine maybe if someone changes some of their logic, they may forget to change here, right? Or you want to be clear about kind of the assumptions you're making and that kind of stuff, right? So if we're definitely setting full to true, then we want it to be empty beforehand. Okay, so I have a question from chat. I'm going to try and pause to parse. A little garbled, but yes, go ahead. It's okay, go ahead. Okay, yeah, so it's a great question. So the question is, could I, instead of having this single bit register for uh, reg in it, or sorry, for full, which I declared as a reg, a single bit one, could I somehow use the valid construct to kind of roll that bit into this buffer declaration? Uh, you could probably. However, I think this way might be a little better for a couple reasons. But let's talk about how that might look. So I've never done this, but I think we might be able to do something like, this. You can say, hey, reg, valid, and then uint, width.w, right? Okay, so that portion, not too hard. So now buffer is going to be, a bundle, right? It's going to be a dot bits for the data and then a dot ready, right? And so thus when we're, connecting it to things, we'll need to do stuff like that. In this case, one thing that worth pointing out is that maybe you actually would want a reg in it because otherwise it might mark as it was full on startup. But other than that, and then yeah, you probably could say things like buffer dot, valid, colon equals true. So yeah, you could probably do something like that. In some ways, it's an interesting idea, right? Because now it makes the connection between the full and buffer very explicit, very clear, because it's dot valid versus dot bits. I personally haven't seen many instances of Chisel code people have used valid or decoupled inside of a register, although I believe that should totally be possible. Yeah, this is a provocative suggestion. I'm still thinking about, the coding trade-offs. Like I said, the thing that worries me at first is making sure we initialize the dot valid equivalent of full to be 0. In terms of the hardware, it's going to be the same, right? If I have a width bit register and then an extra bit for valid, it's the same as having a width bit register and extra bit for full. So hardware-wise, it's going to be the same. Question is just, would we find that code declaration a little bit more clear? There's something to like about it. I do like the idea of kind of associating the valid directly with the buffer, right? It makes it very clear. Yeah, I imagine we can make this to work. Yeah, interesting idea. Thank you. Cool. Great question. Yeah. Hopefully I didn't break it. Oh, I still broke it. Buffer.bits. There we go. Yeah, so it probably could work. Cool. Yeah, I'm gonna keep thinking about this, right? We're having the valid associated directly with the register. Yeah, I do like that. Maybe I'll write this up after lecture and see how it looks. Okay, so given that, base class, we go ahead and create some of our own concrete child instances, right? We can do an add, sure. And so here it's got to find a Chisel function to, override that one abstract method, right? So because this method was given no implementation, it's called abstract because, it's nothing there. But just because it's an abstract class doesn't mean we can have concrete things inside there. Okay, so we go ahead and let's say, we say you want to add, we want to subtract. And so, yeah, if we want to go see the Verilog we get out, maybe I'll zoom out for a second. We can see things like, here it's creating all this work, right? And of course, because it's decoupled, it's kind of all these different cases it's handling for the signaling, but deep inside it, we can find the plus, right? There's the plus. But if you're realizing, wait a second, like how did I do this? Well, here I'm using some stuff we covered before. Here we're using our companion object, using a factory method, and we're actually using pattern matching, so we can actually let the user use a character to make clear the operation they want to do, and then we're making it, right? So that's pretty cool. I don't know why it's so grumpy, but let's go ahead and write a test. Sure, you can see the test in this case, right, where it's going to only be able to produce something every other cycle because, like I said, the way we have this code set up where it's kind of, fill the buffer in full and then drain it, fill the buffer in full, drain it. That's why it's coming out every other cycle. So there's data coming out, but it works, right? So that's pretty cool. And so yeah, this is, a pretty concise thing. And yeah, these things are, we can build like a library, like a collection of similar things. And yeah, this is kind of pretty cool use of inheritance, right? And we can remove duplicated code, right? So if you find yourself doing copy pasting, then changing a few things, however you're doing programming, hardware design, when you like copy paste, you should be thinking, how do I avoid this, right? And this is the kind of thing you do to avoid that. I'll go ahead and reevaluate that one. Okay, so maybe we'll go back with any questions on the prior stuff before we go into trades. Cool. So we've talked about, inheriting from a class. We've talked about making an abstract class and inheriting from an abstract class. And we said, you do extending a class, whether it be abstract or a concrete class, you can only inherit from one at a time. And I told you, 10 minutes ago, if you want to inherit from multiple things, you need to do something called a trait. So what's a trait? Well, a trait is kind of the way to let you do multiple inheritance, but it has some restrictions on it, right? So it's kind of the point. It's this additional construct that allows you to, have some restrictions placed on you, but also some additional capabilities, right? So there's a trade-off, right? And so, for example, a trait cannot take in constructor parameters, right? So it can kind of define things, but if you want constructor parameters, you can't do it. And so the idea is, when you think about what a trait is, rather than being your full-on parent, it's more just, oh yeah, it does so-and-so, right? So actually sometimes you'll find these traits are a great way to get some functionality or something you might want to kind of mix in, right? So first, we'll actually go straight to Chisel then. Okay, so let's say we're going to go ahead and maybe as part of our debugging process, we want to inject some stuff into all of our modules, right? And so what can we do with that? Well, let's say we want to associate some sort of print statement with our modules, right? And do that kind of a very clean, nice way, rather than kind of reinventing the wheel and always, doing this when, and it's kind of gross. What if instead we're able to kind of share this, right? And so, yeah, we can go ahead and make this trait, print in simulation or print in sim, and we can extend it. And then, as long as we, fill in this abstract field, we don't need to worry about the rest of the stuff, and we get the benefit of it, right? So, initially it's false, and then I'm saying true. Do go ahead and print. It's saying, hello from counter. That's the message we told to print. Couple things to point out, right? Here we have a multi-IO module. That's a different class we've been extending so far. We've been extending modules so far. So what multi-IO module does is it allows us to have multiple IO fields, right? So this IO field is called something different. Normally we call our IO, IO or something. But the thing is, when you use this, object apply method on it, you can only do that normally once per module. If you want to do it multiple times, what you're going to want to do in this case when you are extending with a trait, you're going to use something called a multi-IO module. And so yeah, so why would you have this functionality in Chisel? Why not just always let modules have multiple IOs? Well, it might be a bug normally, right? Maybe someone got, code commented out that shouldn't have been commented out or something. You want to kind of have the IO be one clear thing, whether it be they write the bundle inline or they, instantiate a bundle declared elsewhere. You want it to kind of be very clear. And in the common case, that makes sense, right? But, for those that need to have declare IO multiple places, and one reason why you might declare IO multiple places is because you're inheriting a portion of your IO, not the entirety of your IO, then you have multi-IO module. Another thing to be aware of is that this is one of the kind of challenges of object-oriented programming in general, is that sometimes you're going to have functionality that's going to be triggered by the inheritance that may not be visible in the code thing you're looking at. So right here, for example, if someone's reading this, they just see message hello from counter, but if they're trying to find a printf, they're not going to find it, right? So once again, as I said this before, right, be really conscious of what you're inheriting from, because there will be, things that come from these things you don't see here, right? So again, the reason why it's good to have, an IDE, you can go ahead and, right-click on one of these and go take into implementation, right? So yes, that kind of covers that. I saw a question about a coupled factory from the prior slide. I'll go back to that in just a second. But are there any questions on the trait for now? Okay, let's go back to the prior slide and handle this question about the coupled factory. Okay, so I'm gonna go ahead and parse this. Oh, so the question is, here I am, we defined a abstract class, and we made some concrete children of it, and then in our factory we go ahead and instantiate this, and we say, oh yeah, you can't make you can't instantiate abstract classes directly. You need to inherit from them and instantiate those concrete children. So the question is basically saying, could I somehow do this, right? And so it's actually a really good language question, which I'm not 100% sure the answer to. Let's kind of talk it out. So the inspiration is, wait a second, okay. When we declare a bundle, we normally might say things like, actually we go back to prior slide. We'll do something like, hey, here's a bundle. We didn't extend bundle. We made a new bundle, and we gave it these fields, right? I forget the exact mechanism, but I believe there's like a reserved keyword for like a field on this class, where you can basically kind of have like gets passed in via braces, the thing that follows it, and so that is actually not so much an abstract class in this case, right? So I'm not positive, but I would suspect that bundle actually is a concrete class, and you're making an anonymous instance that happens to have different fields internally, right? So yeah, that's pretty cool. And the question is, could I do something similar somehow with the factory method here? The suggestion was, what could I somehow perhaps somehow do a new decoupled operator and then do this inline. Def op. I don't think so, but I'll be really curious to find out if there's some way to make this possible, right? A plus B. Yeah, let's see what this error message is. Like I said, I think the bigger thing is the couple operator doesn't implement this method. It takes in the result of these braces. I think it's the biggest thing. But how to do that and how this is possible? Yeah, that'd be a great question. I wish I was in my office where I could go grab my Scala book and look this up. The Monodisc Scala book was the kind of place you'd look to answer this question. Yeah, so sorry I can't answer this question fully, but that's a good question. Okay, so here we use the trait, have this, configurable printing hardware functionality we kind of inject into our module. So in this case, here's a module which includes hardware, hardware and simulation, that wasn't declared in here. It was only brought in via this, inheritance. But in this case, we're inheriting just a trait, so we actually can do multiple such inheritances, right? So here's the inheritance via class. Here is using a trait with width, right? So look at someone's, more complicated Chisel code. You'll never see extends more than once per line because you're looking to inherit from one class. You may see, with more than once per line because that's, you can have more traits. Okay, good questions. All right, so then um, for templating types, right, or sometimes referred to as generics, right, is possible in Scala, and we're going to want to do that in Chisel to have, this super, super, super parameterized generator, right? And so this can get really deep, really fast in like the programming PL type theory kind of stuff. You talk about covariant types, contravariant types, all this kind of stuff. We're going to sidestep a lot of that and just kind of couple practicalities I'm going to point out when doing this kind of stuff and what's going on. So the goal is to say, hey, I don't know the type and I'm making this module. I'm going to take some sort of parameter or a template for that type and then use that type later on. That's the goal. So what are all these headaches we're talking about? Well, when we look at how this looks in the code, it actually isn't so crazy, right? So here in this case, I'm trying to do a pass-through that the thing is passing through is templated. Doesn't look so crazy, right? Here's the module and here's the type I'm using, right? And that Chisel standard library queue does this. We're going to do that to our own queue in a few minutes. So actually, despite the scariness of the implementation, the usage actually is pretty nice, right? So what's going on? Well, there's two portions, right? There's the templating and then the generator constructor for the type, right? So because the kind of where it's embedded DSL and our when we say types, there's really actually just objects being passed around. We need a way to get to that, and so yeah, we're gonna need to have the user pass in a type, so to speak, right? When it turns to how we're actually templating our code, we will use, notice how this thing, the type is left as T, and what's T? Well, T is defined right here, right? So T is the templated type, and it's going to associate these two together and do that. And then, of course, in the code, we want to use that type. We can, use gen rather than T. So, perhaps if you're writing this the first time, you would think, oh, don't need this gen, and then I have to use T here. For Scala uses of parameterized types, that is how you would do it. But since Chisel kind of has a little bit this fancy with DSLs, we can kind of do it this way. This is a little confusing. You can just kind of treat this as boilerplate and kind of just mimic this. Another thing to point out is this little doodad, right? So what's going on over here? So what we're saying is that this type T we're taking in this parameterized, it can't be anything, right? It needs to be some sort of subclass of Chisel 3 data, right? So Chisel 3 data, that is the base class in the Chisel type hierarchy, right? So here's a similar diagram for the Chisel type hierarchy. And you can see there's internal types that we normally don't instantiate in our designs. Then there are already Chisel types that we definitely do deliberately instantiate, things like uint, sint. Oh wait, bool comes from uint, right? Vec we recognize, bundle we recognize, right? And interesting, vec and bundle, despite seeming very different, right? One has named fields, one has numbered fields. They're both some sort of aggregate, right? As you can kind of see how all fits together, right? But so the reason why we're doing this is otherwise someone could say, give me a generic pass-through on, Scala Boolean or a Scala string, right? And that won't make sense in hardware. So in this way, we're kind of enforcing it to be hardware. So you can just copy this kind of code and not worry about exactly how it works. The choice punctuation here is that thing I was describing a minute ago, how Scala is this very sophisticated system in terms of you can put all sorts of what they call type bounds. You can basically say, oh, I want, types that, are a parent of this or a child of this or a child of this under these circumstances, right? That's where this covariant, contravariant, that sort of kind of stuff comes into play. So this is kind of maybe a good starting point. I'll come to one other detail in just a second, but I'll pause here for any questions so far. So to recap, doing templated, generators, really we're going to just kind of copy this portion in, make sure the user passes in the actual, type you want, and then you just use the thing they passed in. It's going to do the right thing, hopefully. There's one other issue, right? And that is sometimes you'll write your own templated code. This happens more often when you're writing templated code purely in Scala than with Chisel sometimes. And you'll see some compiler error and you're like, what the heck is that? And here it's saying it can't resolve this type, and it's templating the type erasure. And you're like, what the heck is type erasure? Um, and if you go, I've linked to a blog post here. You can find a few other blog posts. It's this really interesting is a generous term, really nuanced situation that's emerged where due to choices made when making Java a long time ago, Scala got put into a certain corner and they made certain choices, right? And long story short, the issue is in some cases, based on the way objects are passed around, once it's compiled down to the Java bytecode and the JVM, later on, if things are too templated, it can't figure out what classes it's being held, it's dealing with, right? And that's kind of frustrating because you want to have things be totally parameterized and generic. And wait a second, I can't do that. You can, as that blog post will show you. There's a way you can add an additional include, as well as add a field to your function calls that will basically pass around a tag that labels what class the thing is. I don't particularly like this situation or the solution. If I was designing Scala myself, I perhaps would have chosen to do this implicit carrying of the type tag always, rather than make the users kind of opt into this. The reason why it's not always on is for performance reasons and size reasons. They don't want to be extra verbose and kind of carry on all this extra stuff. But it can cause some really confusing errors for programmers if you haven't seen this before. And it's kind of a bit of a historical detail. You might wonder, well, how did this occur, right? How does the situation arise in the original Java virtual machine? There was a choice made when they added generics into Java that, well, generics are really cool, but the original language in JVMs did not have generics. And so to have the new version of Java be able to run on these older JVMs, because at that point backwards compatible is very important, they decided to kind of not include that type information, right? So it's kind of stripped away, right? And just like I said, so Java also has this problem. And as a more interesting tidbit, the person that made that choice for Java is actually the same person that created Scala, and that's Martin Odersky. So if you want someone to wag your finger at, that's the person. This is probably my least favorite wart inside Scala. But yeah, and so it's, like I said, when it came time to deal with this in Scala, I would have said, you know what, this is a mistake Java made. I would just always pass around the implicit class tag. If this comes up and you get a really weird type erasure error message, you should go ahead and Google search for it and find this blog post or find something similar to it. A student had a very good suggestion in chat to put in. So maybe the reason why Scala didn't always pass around this implicit class tag is perhaps that might hamper Java interoperability. That's a very good suggestion. Yeah, that's probably also one of the reasons. Because Scala, it's supposed to be able to operate perfectly well with Java code. Most stuff I do purely with Scala. Occasionally we will have a dependence that's a package, from Maven that's in Java. A lot of our auto-grading infrastructure, for example, is in Java. And it does interoperate well. So perhaps, this implicit class tag, if you always had it on, that might break some stuff. Good point. Cool. Yeah, so like I said, this all sounds really complicated. Long story short, when you want a template type, you can do it like this. And here we did a uint. If I did, an essent, not gonna look any different in Verilog, right? But we could also, for example, even define, our own bundle. Actually, I forget the. I always get my braces wrong, so I'm gonna go back and find an example of one of our things. You can see even professors have poor memory. Yeah, new bundle brace. Okay, I was right. New bundle brace. We can say A is gonna be, a uint that's 4 wide, and maybe we'll have a B that is, 2 bits wide. Boom, right? And so, it did do a templating, right? Where here, we have a new type. In this case, it's an anonymous bundle. And it does the stuff for us behind the scenes. So let's go ahead and drop that into our queue, right? So from V6, the only thing missing was templating the type. Well, now we can just do that, right? We can go ahead and put in that boilerplate code I was telling you to put in. Make sure your diddling with a hardware object. Maybe depending on the semantics of your usage, you don't want it to be a chisel data. And maybe it's too broad. Maybe you want them to be restricted to giving them an element. You don't want a collection. Or maybe you want it to be even more restricted than that, perhaps, right? And then you also need them to give them the type generator, and then you go ahead and use that where you do it, right? And you see how we use it not only for the interface, but also when we're declaring the memory. And otherwise, the code's the same. And so there we now have a, parameterized, type parameterized, I should say, Q generator. So we can go ahead and redefine our module and our test case and run it, and it still works. So that's pretty cool. We've parameterized that. Cool. Any additional questions I can catch? Okay, so I did want to spend a couple minutes at the end of today's lecture to kind of introduce the project, right? So we actually have not only homework due next week, but a homework due the week after, but I want to give you adequate time to start thinking about the project and kind of anticipating the project. So in terms of absolute volume of Chisel in your final project, it's not going to be gigantic, right? People go, oh my gosh, it needs to be a really big thing. It's not going to be gigantic, right? People ask me for ballpark size for the complexity. I say 1.5x the more recent homework problems. We've seen in the homework 4 we posted last night, the final form, right? That final Matmul module, imagine that, maybe only 1.5 times bigger. It's a good ballpark, right? Approximately. It's very, very approximate. But understand that, these homework problems, we've been doing a lot of work for you, right? We've been giving you well-specified problems where we really know what we want you to build. We're giving you a lot of testing infrastructure already kind of written for you. And there's also a lot of work we went through as staff actually developing these, right? We actually tried writing a module and seeing what makes sense, writing a tester for it. Oh, it doesn't make sense, changing the interface to the module. So we actually kind of already went through this Agile process, and then we kind of, blanked out some key portions of implementation, asking you to fill those in, but you're kind of only doing a one-shot thing, right? And so the whole point of this project is really to get experience with that evolution, right? That not just the iterative improvement, but the evolution, right? Realizing, you have a plan and you're gonna need to change the plan, right? And so for doing these projects, you should do it in pairs or individual. We're not gonna force the work of anybody. The workload expectations scale accordingly if you're doing it alone versus in a pair. An idea is they want you to build a Chisel generator, right? And so think of some hardware component you want to, have that parameterized ability for, right? And you can see here I have, a long list of italicized verbs. And that's kind of the point, right? You're going to kind of, go with this generator. You're going to propose it. I'm going to give you feedback. You're going to go ahead and design it, develop it, test it, optimize, and revise, and document, etc., right? And so, it should be fun. And hopefully something kind of you find interesting. So if it's something you always wanted to build, we can do that. If you're totally stumped, like I have no idea how to pick a thing to work on, we have some ideas we can share. Or actually, I'll probably go ahead and share some in Slack and make it even simpler. And additionally, if you want to talk to me via office hours or via Slack before some of our deadlines, saying, you know what, I want to just run this idea by and get some feedback, and maybe we can kind of brainstorm something together. Yeah, very happy to do that. Cool. So what's the approximate timeline? Well, we're in week 5 of the quarter right now. Next week, try to start getting an idea of what project you want to do and find a partner and start brainstorming it. In week 7, what's going to happen is you're going to submit a one-pager of just of what you're proposing to do. And the one-pager of the proposal is going to be really simple. It's basically just saying, here's the generator should look like. Here's what's going to, here's the functionalities for it. Here's what we expect the kind of knobs to be. Here's our plan to get a minimum viable thing working, or how we're going to close the loop early and how we're going to kind of incrementally build onto it. Just because you have a plan origin doesn't mean you can't change it, right? We're going to be agile. And we're actually going to have mini, feedback meetings with the staff to kind of get some discussion about your process and give some suggestions. And the goal is, to have you get some small version of it working really early, right? And then kind of continuously going on to it, right? So rather than having this, oh my gosh, feeling of the night before it's due, like all or nothing is going to work or not work, we don't want that, right? And that's not the agile process we're going for. We want you to kind of get something really small going and keep improving it. And when you get close to deadline, the question is just how many times have you had a chance to improve it and revise it. But let's say your most recent attempt for a new feature or a new optimization doesn't pan out. you can still revert to something that's pretty good. It's just not as optimized as you were hoping to go for. And yeah, so you can see kind of process. Okay, you're going to close the loop early. You're going to keep, close out the features, keep revising it, and then you're going to do a mini presentation to your classmates and be done with it. And then one detail not listed here is that not required, although we highly encourage you to open source your output, right? So you go find the courseware page from the last time this course was offered. I've linked to the student projects from then. All groups, voluntarily posted it publicly on GitHub. So you got a kind of sense for what people have done. You may notice that last term, a lot of projects were all ciphers, from cryptography. The reason why is our homework assignments last term were also mostly ciphers. And so people kind of got in that cipher mindset. This term, we've reduced the number of ciphers. I think they're really interesting. So there's plenty more cryptography algorithms to implement in ciphers if you want to do that. And so, yeah, that's something to consider. Cool. Okay, so to make this more concrete, like I said, you're going to have a proposal at the start of class time, in over a week of kind of what your thing is going to do, and write a little bit more instructions, put on a website about what needs to go in this document. But mostly, it's just you should have an idea of what you're trying to build, and then how you're going to kind of go about doing it, how you're going to make this more reasonable, and perhaps is there any resources you can take advantage of. I'm going to momentarily pause from the schedule to answer a question from chat. I only know how to do our Chisel code through a tester framework. Is that enough to validate? Yes, yeah. So for this class, using the Chisel testers where we're kind of, doing some behavioral testing, that's sufficient, right? You've seen me kind of move into this mode where we do things where we will perhaps build a Scala functional model, and then you kind of do code simulation and compare it to. That's no better than nothing. It's not hyper rigorous. One thing I am really excited about this term is we're still producing this. We're hoping to have a guest speaker come in and introduce the functionality added in Chisel 3.5. One of the really exciting features added in Chisel 3.5 is actually a backend to do some amount of formal verification. So we're going to have a hopeful guest lecture and mini lab exercise based on that. We're going to try out that formal verification backend, and perhaps you'll enjoy that experience and you'll do that for your project. But that will not be a requirement. That's just something that hopefully you will opt into. But yes, in general for testing, depending on the nature of your generator, if you can just be really exhaustive of how you're thinking of the various test cases, perhaps you can have that Scala functional model and co-simulate and generate a lot of comparisons. Yeah, that's the kind of thing to think about. I know that there is another form of testing this student is worried I'll be asking them to do. I'll let them respond in chat. Going back to the schedule, so you're going to send us your proposals. We're going to meet during class time. So rather than trying to schedule, when are people available, we're just going to sacrifice 2 lectures to having a group meeting. So depending on when your group is scheduled, you'll be one lecture or the other lecture. And then, so then there's going to be an intermediate deadline. We're going to ask you to send a link to GitHub. It can be private. It can be shared just with the instructors' GitHub accounts that shows something working, right? Can be feature incomplete, right? So it can be something that, we said we're going to do X, Y, and Z, and we only do X and Y so far, but we're going to do Z. But yeah, here's an example of that code, compiling, and here's an example of it passing a rudimentary test. That's what we want to see. Perhaps more than that, the more you get done by there, the better, right? But kind of as an initial, stopgap, we want to see you close that loop, right? Have something working with some amount of functionality and share that with us, right? Then you're going to do presentation in class on the last week of the quarter. These presentations will be, remote via Zoom to each other. I'm not going to put these on YouTube, so don't worry. Although I guess if you're really proud of your work, you're happy to record it. I'd be happy to record it and post it for you if you'd like. But yeah, so we'll have our presentations, and then the following Monday is going to be kind of your, final submission, right? So at that point, you're going to have your finalized repo, and then rather than writing a very big report, I'm fine with kind of a PDF slide deck created by some presentation software, PowerPoint, Google Slides, etc., that kind of talks us through what you've done. And it'll basically be your presentation you gave the week before revised, right? So, you give a presentation to us, we'll email you some feedback, and then you can go ahead and revise the presentation to kind fix any issues, and you send that final thing to us on the Monday of the finals week, and you're done. That's it. So yeah, to kind of recap, we're looking at, homework 4, there will be a homework 5, there will be a lab 5, and then a lab 6, and maybe a 6.5, but these later labs are going to be really kind of short, kind of in the background compared to your project, right? So for now, focus on lab 4 and lab 5, homework 4 and homework 5 when it comes out next week. We'll go from there. Cool. Any other questions about the project? Well, great. That's all, folks. Have a good day.